Right. Hi. So I invite you to ask questions via the Piazza post. You can also raise your hands and unmute yourself, and I will be happy to answer any questions that you have along the way. All right. So let's start. Okay. Right. So let's recap what we discussed last time. So we talked about this problem called set cover. It's a very important problem. I told you that if you solve this problem, you would get $1 million, and I meant it literally. There's an institute that offers $1 million if you solve this problem in tournament time. Okay, so we will not do it today, otherwise I will send them the solution. But what we'll show is we'll show how greedy works for this problem, and we'll show that it's not giving the optimal solution, but it's giving something not too bad. Okay, and actually this is not like a very special case. There are many problems that are sort of very hard to solve optimally, but greedy give us some approximation of the optimal solution. So sometimes it will give us a solution that may be twice as, uses twice as much resources as the optimal solution. Here, it will be a little bit worse than that. And in many cases, these are like the best algorithms that we know. So greedy algorithm are sometimes the best what's called approximation algorithms. And this is one example of that. And we will talk about it later in the course when we talk about NP hard problems and how to cope with NP hardness. Okay, so this was sort of like an introduction, but let's now dive into the details. We're talking about set cover. What is it? We have a universe of n points. Okay, so you have here this example where you have 4 points. And you also have a collection of subsets, S1, S2, S3, up to Sm. Each one of these subsets is the subset of the points. And you are also guaranteed that if you take the union of all subsets, then you cover all the points. So every point is covered by one of these sets. And now you want to find a minimal sub-collection that covers the entire universe. So for example, you have these 3 sets here, S1, S2, S3. If you take S1 union, S2 union, S3, then obviously you cover everything. This is what sort of the assumption. But can you find a smaller covering? Can you cover it with less sets? And the answer is that in this case, yes, you can cover it if you take S1 and S3, for example. So you can take 2 sets. And can you cover it by 1 set? Well, you look at it and you see that no, right? Because every singleton, every single set avoids at least 1 point. Right? So 2 is the optimal solution for this case, but this is really a small example. This becomes harder and harder when we take more points and more subsets. Okay, so what do we want to minimize? We want to minimize the number of subsets. So we denote by J, the collection of subsets that we chose. Okay, and we want to pick the minimal J such that the union over all Sj, where little j is in capital J, where this covers everything. Okay, so it's sort of like a very mathematical way of saying, we just want to pick the minimal number of sets that cover all points. Okay, and the greedy strategy was, the most natural greedy strategy is to, pick first the biggest set, and then look at all the, what we haven't covered, and then pick the next set, which covers the most new points, and so on and so forth. So every time, pick the set that gives you the most new points. Okay, that covers most new points in your universe. So in this case, it would work like, for example, we can pick S1, covers 3 points, and then the only point that is not covered is 4. So then the next iteration would pick S3. So in this case, greedy would probably work, but we had an example where it doesn't work. Okay, so this is how the algorithm, how you can spell out the algorithm. So you start J with the empty set, and while you haven't covered everything, which is sort of this check, you check whether the union of all sets in J equal U. If it doesn't equal you, then you continue. If it equals you, then it means that you already covered everything. And now every time you're going to pick the set SI that covers the most new points. And you know how you write it mathematically, it's just the one with the largest size of SI minus all the elements that you already picked so far. Okay, and I have this notation S capital J to denote the union of everything that we covered so far. Okay. So at any point in time, we are picking the set SI that has the most new points, and eventually we cover everything, right? Because right, we know that there's a way to cover everything, so this loop would end. And the question is it a correct algorithm? Does it solve optimally the problem of set cover? Do we win $1 million? And the answer is no. And we have a very simple counter example. So this is like a turtle or a sunflower. So notice this, in this example, we have, 5 sets with 2 points and 1 set with 5 points. So if you think of it as a flower, then all these, small sets with 2 points are like the leaves of the flower, and you have also the core of the sunflower. Okay, so what will the greedy solution choose? The first set that it's going to choose is this set, right? Because this set is the biggest one. So we are picking this set, and now we are screwed because actually we have to pick all other sets, right? We notice that we have to pick this one because this element is covered only by this set and this one, right? So greedy solution would actually pick all sets to cover the universe, whereas the optimal solution is just to pick the 5 smaller sets. So greedy sort of led us in the wrong direction. He sort of told us better to pick the large set, whereas really we should have not picked the large sets. Okay, so greedy doesn't work in this case. All right, so what do we want to say about it? What there is to say. So greedy doesn't work. We don't know of any algorithm that works. If we would have known, then this millennium problem would be solved, because this is an anti-hard problem. So what we will settle for is the following theorem, that the greedy solution is not too bad. If the optimal solution uses k sets to cover the entire universe, then the greedy solution uses, at most k times log n plus 1 sets. Okay, so you can think of it as if you have all possible ways to cover a set. K is the optimal, like picking k set is the best way that you can do it. Everything below it is impossible. If you pick all sets M, then this is just a trivial solution, right? All sets cover the entire universe, so that's a trivial solution. And what our algorithm is doing, it gives us something here, like k times log n, ln n. Okay, so it's not as good as optimal. It's not even like a constant fraction, but it's a log n factor away from optimal. Okay, and in fact, even improving this, like if you have an algorithm that gets a better guarantee, for example, gets k times square root log n, okay, this would also solve the millennial problem. So there's a very interesting reduction that shows that if you can approximate it to a factor which is better than log n, then you can actually solve it completely. So that's a very interesting thing that we will not cover in this course, but just to say that even improving it slightly, to get this guarantee slightly better than what is known, would already be a huge deal, and would solve the P versus NP problem. And therefore, it's probably hard. It's probably impossible to do so. Yeah, +1. Yeah. Yeah, I'm more pedantic about this +1. In the book, it's not written, so I mean you can ignore it if you want to. All right, so let's prove this theorem. This is going to be it's sort of like a short proof, but it's kind of tricky and it has like a lot of interesting ideas in it. Okay, so how can we prove this? So in order to claim that greedy is solving it in, covers all the points while using at most k times log n sets, what will be useful for us is to keep track of how many points we covered so far. Like at every time step to notice how many points we covered so far and how many points we haven't covered. Okay, so we keep track of the number of points we haven't covered after t iteration. Of the greedy algorithm. Okay, so what do we know? We know that there's the optimal solution, but we have no idea how someone came up with this optimal solution. We just know that it exists. And just by its existence, we're going to say something about how many iterations greedy has. Okay. So this is a little bit vague. Let's see what do I mean by that. So initially n0, what is n0? How many points are uncovered after 0 iterations? So that's just, all the points. And we assume that all the points, that the number of points is n. Okay, so n0 is n. And what we'll show that nt decreases rapidly. It decreases rapidly, and this would allow us to show that, after not too many iterations, we cover everything. What does it mean that we cover everything with this notation? It means that nt equals 0, right? If we cover everything, then there are no more uncovered points. Okay, so that's sort of the strategy. So let's look just on the first step. Okay, I want to claim that n1 is significantly smaller than n0. Okay, so let's be a bit more precise about that. So I want to claim that n1 is at most n0 minus n0 over k. Okay, it's strictly below n0, and by how much? By n0 over k. And why is that? So let's look at our entire universe U. Right, it has n points, right? What do we know about these endpoints? By the assumption on the optimal solution. We know that there are k sets that cover all these points. So there must be like k sets. I don't know which set there are, but let's imagine that we draw these sets. So there's like the first one, second one, the third one, and the fourth one. Let's say k equals 4. So there are like 4 sets that cover all the endpoints. What do we know about the biggest set in this sub-collection? What will be the size of it? Right, so every point is covered by one of these sets, and we have k of them. So it must be the case that one of these sets cover at least n over k points, right? Okay, so since optimal solution uses k sets, there exists a set in it that covers at least n over k points. Right? It's sort of like pigeonhole. if every set in this collection covers less than n over k points, then overall you cover at most, less than n points, so you don't cover everything. So this cannot happen. So what does it mean? It means that there exists a set which is kind of large. It's of size n over k at least. And what does greedy do? It picks the biggest set. Greedy doesn't know what the optimal solution is, right? If it would have known, then probably would have picked it. It just picked the biggest set. And we proved that the biggest set is of size at least n over k. Right? So greedy picks the biggest set, largest set, which is of size at least n over k, right? So therefore, the number of uncovered elements or points after the first iteration is at most n0 minus how many we covered by this largest set, which is n0 over k. Okay, so this is the first claim. So we showed that in one step, we went from n to n minus n over k. All right, is this clear so far? Any questions on that? All right.
Professor, I have a question.
Yes.
Can you explain what exactly the K is? I'm not really sure what K is.
K is this thing, right? I'm assuming that the optimal solution uses K sets. That's part of the theorem statement.
So like, if you want to run this algorithm, do you already like kind of know that optimal solution is
No.
K?
The algorithm doesn't use K. Only the analysis uses it.
Oh, okay.
Right? I already gave the algorithm earlier. You just pick in every point in time the biggest set, or the set that covers the most new points, right? So that's the algorithm. It doesn't need to know K.
Thank you.
Right. So sometimes, by the way, sometimes we would have, like later in the course, we would have some kind of what's called decision problems where we are given a parameter, maybe K, and then we need to say, is there a solution with using K sets or not? So this is not the case here, but sometimes this K would be part of the description of the problem, but not today. Right? So K is just for the analysis. All right. So this is good. We sort of made some progress. Like in one step, we went from n to n minus n over k. Okay. So, but we don't only make one step. So I want to claim something more general than that. So I claim that in more general, nt plus 1 is at most nt minus nt over k. Okay, so whatever you did in the first t iterations, okay, that's good. You did what really did what it did, and it left nt points uncovered. And now I claim that in the next iteration, the number of points that will be uncovered is at most nt minus nt over k. How can you prove that? Can someone suggest proof for that?
The NT points are covered by at most K sets.
Exactly. Excellent. So it's exactly the same proof, but we're going to only look at only the points that we haven't covered so far, right? So let's look again at our universe. So Greedy already picked a collection of sets. So Greedy did like something like that. It covered this thing, and then it covered that thing. So maybe this is what Greedy did. Okay, now we have a bunch of points that we haven't covered. How many? So I'm just immediately after the t iteration, there are nt points that we haven't covered. But what do we know by the assumption on the optimal solution? We know that the optimal solution must cover all these points. And the optimal solution has k sets. So, right, so the optimal solution maybe have these, I don't know, these k sets. Maybe some of these sets don't cover any points. But we know that, optimal solution covers these endpoint, NT points. Therefore, there exists a set that covers at least NT over K of these points, right? And by these points, I mean the one that weren't covered by greedy before. And greedy picks the set that covers the most new points. So it will in particular pick a set that covers at least NT over K. Maybe I'll make it a little bit more clear. Okay, so greedy picks a set that covers at least NT over K points, right? So it's basically the same proof, but we are just looking at it a little bit in a more refined way. We are just looking at the points that we haven't covered so far. Okay, so we finished claim 2, and everything from claim 2, everything would follow by some, simple calculations. So everything from now will be simple math, right? So we will not talk about algorithms from now on. We will just talk about math. Okay, so what did we prove? We proved that NT plus 1 is at most NT times 1 minus 1 over K, right? Let me write it differently. Okay, let's do it like that. Okay, and then, this is a recurrence, so we can solve it, and, we can get that this is actually N0 times 1 minus 1 over K to the T plus 1, right? So wouldn't it be nice if this number would be smaller than 1? Would be nice, right? Why it will be nice? It will mean that after T plus 1 iterations, we covered everything, right? So that's what we need to figure out. When is this number smaller than 1? All right? So that's just a simple mathematical question. So when is this number smaller than 1? So, okay, I'm going to simplify it a bit. So 1 minus x is always smaller than e to the minus x when x is non-negative. So this is, and n0 is n. So this is n times e to the minus 1 over k times t plus 1. Okay, let me. All right, so that's just a simple inequality that you can verify from yourself, right? That this holds for any real x, and we just need this to be smaller than 1, so it suffices that t plus 1 over k is bigger than ln n. When t plus 1 over k is bigger than ln n, then we have e to the minus something bigger than ln n. So this will be smaller than 1 over n. And therefore, the entire thing would be smaller than 1. So you see that, this is equivalent to saying that t plus 1 is bigger than k ln n. So we can just pick, t to be k ln n floor, and then t plus 1 would satisfy this. Okay, so this is the end of the proof. If we pick these many sets, then we are guaranteed that we covered everything. Okay, and we use some very basic inequality from calculus. If you are not comfortable with it, maybe it will be a good idea to review it after the lecture. Another way to say it is, t plus 1, you can write it as t plus 1 over k times k, right? And then you have 1 to the 1 minus k to the k times t plus 1 over k, right? This entire thing. And this thing is smaller than 1 over e. So that's another way to see it. Okay, I'm just going to erase that because it's not important for the proof. But if you don't see why this is correct, then this is another way to derive the same inequality. Okay, so any questions about that?
Why is the exponent 2 plus 1 on the very far right side?
2 plus 1.
T plus 1.
T plus 1. Because I use n to the t plus 1. So yeah, this was maybe a bad choice, right? So if I would start with nt, then it would be t. But right, so just because I start with n to the t plus 1, and then how many steps do I need to get to n0? T plus 1 steps, right?
Well, how does 1 minus 1 over k turn into e to the power of t plus 1 divided by k?
So again, the question is, why is this correct?
Yeah.
Okay, so I justified it, right? I said 1 minus 1 over k is smaller than e to the minus 1 over k. And then you raise it to the power t plus 1.
Oh, okay.
Right, so that's just true for every number. And then if you raise it to the power t plus 1,
All right. Thank you.
Could you please repeat why we have the t plus 1 over k is larger than natural log of n?
I mean, it suffices, right? So we want this entire thing to be smaller than 1, right? So for this to be smaller than 1, it suffices that, okay, so maybe I should have derived it slower. I'm sorry, yeah, I'm not focusing on this because this is like calculus, so it's not really the main part of this course. So I assume that you're comfortable with it, but maybe I should do it a little bit slower. Okay, so let's erase everything. Okay, so up to here, we verified everything, right? So n to the t plus 1 is at most n times e to the minus t plus 1 over k, right? So I said that it would be nice if this right-hand side would be smaller than 1. So, right, so I want to know when is this thing smaller than 1? Okay. So now it's just manipulation. So let's, multiply by e to the t plus 1 over k. So this is the same as e to the t plus 1 over k bigger than n, or t plus 1 over k larger than ln n, right? So this is equivalent to that. Or t plus 1 greater than k ln n. All right. So as I said, it's just math. It's sort of, a little bit we are going to other areas, but it's very simple math, right? It's just multiplying, taking logs.
Oh, Professor, stupid
Yeah.
question, but why does n0 times 1 minus 1 over k have to be less than 1?
That's what we want, right? Why?
Oh, why though?
Because then we covered everything, right? What is nt plus 1? It's how many points we are still not covered. If this number is more than 1, right, it's an integer, so it must be 0. So it means that we covered everything.
Oh, so we're just proving that that's an integer.
Can you say it again?
Oh, this is like the base case. So like if it's less than 1, then it has covered every point. So that's just the argument, right?
Right. So we
Okay.
try to understand when is the first point in time where nt or nt plus 1 equals 0. Okay, and that's how we derive it.
All right.
We derive it by saying, okay, maybe let's look at it. Maybe this was a little bit complicated. Let's say that k equals 2. What would happen? K equals 2. It means that there are two sets that cover everything. Okay. Well, first we can probably find them if we do some kind of brute force. But let's say that we are not doing it. We are doing greedy. So what do we know? We know that every time we do greedy, these two sets cover everything that was uncovered so far, right? So every time we would cover at least half of the uncovered points, right? So this would tell us that, how are these numbers progressing? If k equals 2, then we know that nt is smaller than nt minus 1 multiplied by half. So how many iterations would we need until we covered everything? Log n, right? We started with n points. Every time we know that we cover at least half of them, so we need log n iterations. So this was just a special case where k equals 2, but when k is arbitrary number, then after roughly k iterations, we would cover sort of like a constant fraction of the points, and then we need to repeat it log n times to cover all the points. So this is what's going on here. And you can see that we are not really getting the optimal solution. Like the optimal solution in this special case was 2, but we got that, n log n was equal to 0, meaning that after log n iteration, we covered everything, which is a lot worse than 2, right? But that's what we can guarantee. Okay. Any questions about that?
Professor, I have a question. So you showed previously that like it's hard sometimes, like k is hard to find, right? Like optimal solutions could be NP problem.
Yeah.
But like we're assuming like we could just find k as if it's like you just find it. Like could there be like problems involved with that?
Yeah, so I said that k is not part of the algorithm, right? The algorithm is not using k. We are only using k in the analysis of the algorithm. Okay, so notice that this is a proof. This is not the algorithm. The algorithm is just picking the largest set at any point. So we don't need to know k, and we don't know how to know k, right? So, but nevertheless, whatever k is, the algorithm outputs a collection with at most k log n sets. Okay, so it's a little bit different than things that you are used to, because sort of the analysis is very different than what the algorithm is doing here. But sort of k is just something that you sort of is a variable that is used by the analysis of the algorithm, but it's not used in the running time of the algorithm. The algorithm doesn't need to know k. The algorithm just picks a set that covers the most new points in every iteration. Okay.
I guess my question was like, so we're saying like k log n is like number of steps we take for greedy algorithm, but like I was like kind of confused how can you say that even if you don't know what k is like to begin with? Do we just assume that like, oh, we know k, and analysis is that like k log n it takes k log n minus 1?
Yeah, so it's not, I'm not assuming that the algorithm does not assume that we know k, right? This is the algorithm.
Yeah, but are we assuming that in analysis? Yeah, I get that in algorithm we don't need to know k, but like
Yeah.
in analysis, like we use k and we output like value involving k log n minus 1, right?
So this is the theorem that we just proved. We proved that if the optimal solution uses k sets, no matter what k is, then the greedy solution uses at most k log n sets, right? So for this proof, we kept track of, we sort of assumed that we know k, because it's a proof. The proof doesn't care about how much time it takes to know k, right? K exists. It's a number that exists. This is the best solution. And we argue that our solution gives us something here, right? The best solution is k. There are maybe more solutions that uses k plus 1 sets, k plus 2 sets, 10k sets. What we claimed is that our solution uses k log n sets. Okay. And to claim this, we sort of used in our analysis this assumption, right? That there exists a solution that uses k sets. So if you want, in the analysis of approximation algorithm or greedy algorithm, you can always assume that the optimal solution has some value, and then you need to prove that your value is at least as good as this value if this is a greedy algorithm is solving the optimal, solving optimally the problem. And if it's not, if it just gives you an approximation, then you need to show that the greedy solution gives you at most some, I don't know, 2 times the optimal value, or here log n times the optimal value. Okay? So, I mean, the theorem is just this one line. This is what we proved. If you have more questions on that, I think we should take it offline, because we need to start talking about dynamic programming today. And we'll be happy to stay here a few minutes later after the talk and continue answering questions about if this is still unclear, right?
Yeah.
Okay, so I want to sort of sum up. So we talked for like 2.5 meetings about greedy algorithms. We saw that greedy algorithms are sort of doing this very local choice at every point in time. They're making something that looks like the best choice locally. And somehow, in some cases, we're able to show that this is the global optimal choice. That if we look at the entire solution, it gives us the optimal solution. We showed that, in several cases, we proved the correctness by sort of looking at any optimal solution and looking at the greedy solution and sort of showing that you can do these swaps or exchanges between the optimal solution so that we maintain its value and we are getting closer and closer to greedy. And eventually we would go from the optimal solution to the greedy solution without changing the value. Therefore, greedy gives you the optimal value. We've seen many beautiful examples. We've seen, Huffman coding. We've seen minimum spanning trees. And today we saw a problem where greedy doesn't solve the problem, but it gives you an approximation of the optimal solution. If the optimal solution was, I don't know, 1,000, then the greedy solution is guaranteed to give you no more than, 10,000, let's say. Okay, so I'm just plugging in numbers. All right, so this is something that we'll see again later in the course when we talk about coping with NP harness, and I think it will be probably more complete after we see it in this context, because this is sort of part of this discussion about approximation algorithms that are very important. Okay. So I want to switch gears and move to the new topic, which is dynamic programming. So dynamic programming is a very useful algorithmic technique. It can be used to solve many problems. In fact, we already saw some problems that, if we think about it a little bit, the solution used dynamic programming. So one example is Bellman-Ford. And another example is shortest path in a DAG. And maybe another example is Fibonacci, but Fibonacci is a little bit simple. So, so you can solve it probably using many, many different techniques. So what's the idea of dynamic programming? The idea is that you want to solve a big problem. Instead of looking at this big problem, you know, and being clueless about how to solve it, you sort of identify sub-problems, such that if you know how to solve these sub-problems that are smaller, it will be easy to derive a solution for the big problem. And then how do you proceed? You just, so it's sort of a little bit like recursion, but how you usually solve it is that you solve all sub-problems. And you start from the smaller ones, maybe ones that are only about, you know, 1 or 2 elements, or maybe if we talk about graphs, it's like sub-problems involving only 1 vertex. And then you start growing the number of, you know, growing your sub-problem size until eventually you get to the big problem that you wanted to solve initially. Okay. So from small to large. So this is, of course, very vague and, you know, not accurate, but you know, this is maybe something that captures how we solve problems using dynamic programming. And an alternative view for this is that dynamic programming is just recursion, but sort of not repeating the same subproblem again and again. So in recursion, we saw that sometimes recursion is really bad. So the idea is to use memoization. And I think the best way to understand what I mean is just to start with an example. So I want to start with the example of, you know, a very simple example that you've probably seen many times, and you already seen it in this class, maybe in the first lecture. So the example is compute the, you know, given n, compute the nth Fibonacci number. Fn. Sorry. Okay, so what will be the sub-problems that will be helpful for solving this problem? The sub-problems would be for I equal, you know, 2, 3 up to n, compute fib I, right? So these would be the, sorry, fi, let's call it. Okay, and the claim is that, you know, when we do it like that, then it's very easy, or maybe even n-1, compute fi, then it's very easy to solve fn, right? So if we solve all the subproblems so far, then what is fn? It's just, you know, fn-1 plus fn-2, right? So that's the recurrence. Okay, so how can we solve all these subproblems? As I said, the main idea is to solve the subproblems from small to large. So we start with the smallest one, right? So we go from I equal, okay, so f0 is just 0, and f1 is 1. And then from I going between 2 and n, we take fi to be fi-1 plus fi-2, right? So that's the algorithm. And how much time will it take us to run this algorithm? Well, we talked about it in the first class. I mean, it a little bit depends how we think of, you know, this operation of adding 2 numbers. If we think of you know, the cost of adding 2 numbers is constant, then this algorithm would take n n steps, right? On the other hand, I mean, it's very natural to implement Fibonacci using recursion, right? So we can check, you know, if n is smaller than 1, then we return n, right? That's sort of like the base case or the edge case. And otherwise, what are we doing? We're returning fib n minus 1 plus fib n minus 2. And that sort of, you know, works by definition of Fibonacci, right? So that's how the Fibonacci sequence is defined. But what would be the problem with this algorithm on the right, the recursive implementation? Yeah, any?
It's exponential.
It's exponential, right? So if we are looking at how many times we will this algorithm, you know, what would be the runtime of these algorithms, then we call, you know, we have like fib on, I don't know, 100, then this calls fib of 99 and fib of 98, and then fib of 99 calls fib of 98 and fib of 97. And eventually, you know, we would go in, up till we get to the leaf. Every leaf would compute like the Fibonacci of 1 or of 0. And the number of leaves would be at least the you know, the n Fibonacci number, right? Because we're just adding, in the end, we're just adding zeros and ones, and we are getting this n Fibonacci number. So this would be exponential in n, the running time. So that's not so good. But how can we look at, you know, how can we modify this code so that it would run much faster? Right, so we can do it using memoization. So I'm assuming that I have some kind of a dictionary or array, which is global, that I'm going to call it mem. Okay, so I'm first checking if n is at most 1, then I'm returning n. And now I'm checking if the answer was already computed and stored in my cache or in my memory. Okay, so I'm using like Python notation, and mem is like a dictionary, okay, or maybe an array. So if n is in mem, then I return mem of n. And what would I do if it's not in my memory? Then I just compute it. Okay, so I'm computing it and I'm storing it in my memory. So I'm computing it using the recursion of Fibonacci. And eventually I'm returning this answer. And now what will happen? Let's say that I run fib m on 100. Then actually the running time of this algorithm would be order of 100 or order n. And the reason is that I'm sort of gonna, you know, run this algorithm for each input between 1 and n. I would run it at most constant amount of times, right? So if I'm trying to run, okay, so fib on 100, then I start, you know, I'm starting to compute fib of 99. So let's say that when this thing ends, now I want to compute fib of 98. But when this thing ends, I already computed fib of 98. So this would take me only order 1. So actually, you know, this tree would look like a very small tree. Okay. I mean, you can convince yourself why every time, like for every I between 1 and n, we would run fib mem on I only constant number of times. Okay. So this was just an alternative view. I will not use this alternative view so much, but if you like recursion and you like memorization, you can always solve DP problems using this approach. And you can sort of convert between the two solutions. Okay. So this was like a very toy example, but I want to show you this example because it sort of demonstrated the idea of dynamic programming, and it's a very simple example, so we can understand it quickly. So another way to view this example is that, let's look at all the subproblems in this Fibonacci of n. So I want to view each subproblem as a node. And I want to connect two nodes with an edge, a directed edge. Okay, so I'm connecting the directed edge from I to J if subproblem J depends directly on the solution of subproblem I. Okay, so let's see an example. So we are talking again on the Fibonacci computation. So we have these vertices corresponding to, all the subproblems. And what will be the edges? So the two incoming edges coming into n will be, n minus 1, n depends on n minus 1 and depends on n minus 2. What does n minus 1 depends on? On n minus 2 and n minus 3. Right, so what would this graph look like? It will look like a path, and we also have these edges that skip 2 steps in every time. Right, so we have, well, 0 and 1 are sort of like special cases. So what can you tell me about this graph of subproblem? Right, so we have vertices and we have edges. What is this graph? It's a DAG, right? It's a directed acyclic graph. Why? Well, first it's directed, right? Because I said that every edge is directed, sort of saying, this problem depends on the solution of this problem. Why is it acyclic? Why is it important it's acyclic? If problem I depends on problem J, and problem J depends on problem K, and problem K depends on problem I, then we actually don't know how to solve it, right? So if there's like a cycle, so think of it as if you're like implementing it using recursion. Then, I calls J, J calls K, and K calls I. So we are in this infinite loop, and we don't know how to solve it. So all the problems that we're gonna see can be phrased as solving a problem. You can look at all the possible subproblems. You can identify all the edges, and you better have a DAG. If you don't have a DAG, then you are running into, circularity issues, and you don't really know how to solve the problems. But if you are in a DAG, then you can just use the topological sort and then solve it according to this order. So here it's very clear what's the topological sort, like just the numbers 0 to n, and I'm solving first 0 and then 1 and then 2 and then so on and so forth. And since this is a topological sort, I know that whenever I'm trying to solve the problem I, then I already solved all the previous problem, and in particular, all the incoming edges are problems that are coming from problems that I already solved. Okay. So really talking about graphs and dynamic programming is not that different. And to bring this back to something that is really familiar to you, so I want to review again shortest paths in a DAG. Okay. Yeah, no. All right. Shortest path in a directed acyclic graph. Right, so this is something that we already seen probably like a couple of weeks ago. So let's recall what is the statement of the problem. So we are given some graph G along with some length on the edges. So every edge is a natural length, a length which is a natural number. And we're also given, let's say, two nodes S and T. And what do we want to find? We want to find shortest path from S to T. Actually here, sorry. So for this problem, we don't need this. We can assume that actually we have both positive and negative weights, right? So in shortest path in a DAG, we can handle also negative weights. So I want to notice that we handle also negative weights. Do we need to worry about negative cycles? No. Why? Because it's a DAG, right? So there are no cycles. So not positive, not negative, just no cycles. All right. So we already saw how to solve it, but now I want to look at it again from the perspective of dynamic programming. So, you know, when we look at this entire graph and we look at these two nodes, S and T, they may be very far from one another. So it's a little bit, look a little bit overwhelming at first, at least if we didn't know how to solve it. So the way that we solved it is sort of, we found the shortest path to all, from S to all nodes, right? So we found from S to V for every vertex V in the graph. And this is exactly the dynamic program approach, right? Because this is exactly this definition of all these sub-problems. Okay, sorry, I need to charge my laptop, and otherwise in 2 minutes you will not see me. Okay, all right. So now I'm charging my laptop and everything is okay. So the approach is to look at all these sub-problems. What are the sub-problems? The shortest path from S to V for any vertex V in the graph. Okay, so even if we want to compute the shortest path between just two cities, it's useful to sort of look at the shortest path from the first city to all cities. This is actually how we always did it, right? So we didn't really distinguish between computing the shortest path from S to everyone and from S to T. Okay, so this is just to think about all the subproblems. And now, more importantly, we want to write a recurrence on these subproblems. How we can solve one problem from the others. Okay, and what will be the recurrence? What is the distance to a vertex V? It's the minimum over all vertices U such that UV is an edge. And then I take the distance to u plus the length of the edge between u and v, right? Why is this correct? The shortest path from S to V must, right? So unless S equals V, which is sort of a special case, which we'll handle later, the shortest path from S to V must be of length at least 1. So there is a node which is just immediately before V. So therefore, it suffices for us to just look at the shortest path for all nodes so that we have an edge between this node U and V, and then to take the distance to U plus the length of this edge, right? So this worked for most cases, but we have some edge cases, so maybe, or base cases. So the distance to S is 0. Right? There is only one path from S to S, the empty path. And the distance to a vertex V is infinity if V has no incoming edges. Another way to say that V has no incoming edges is saying that V is a source. I'm sort of spoiling you a solution to one of the questions in the midterm. How do you check if a vertex is a source? Well, you can just check if it has no incoming edges. Right. Okay, and the last thing that we do when so this is sort of a recipe in general for dynamic programming, and the last thing that we do is we analyze the runtime, and sometimes we would care about the memory, how much memory we use. So let's look at this algorithm. So how many steps we'll make in our algorithm? How many subproblems there are? There are n subproblems, right? One for each vertex. How much time does it take to solve a subproblem given all the previous subproblems? So it takes a time which is proportional to the in degree of this vertex V. Right? So if I'm looking at a specific vertex, then I just need to look at all the edges coming into it. So if, for example, I'm reversing the graph, then I can just iterate over all edges coming to V in time, which grows linearly in the number of such edges. And then overall, the running time would be the sum over all V's. And each one I'm paying is a constant times the in degree. But how much, but when I calculate this sum, what do I get? If I'm counting for every vertex in the graph, all the edges coming into this vertex, and I'm summing over all vertices, what would be the total sum? It will be E, right? So this is C times E. Because every edge is counted exactly once. Every edge goes from somewhere to somewhere, and this vertex V counts it once in its in degree, and every other vertex does not count it. So this is exactly order E, or maybe, maybe we need to do like constant work for vertex, no matter if its in degree is 1 or 0. So this is order E plus V. Okay. So I'm sorry, I'm changing it a little bit. Okay, so I'm changing it to be 1 plus the in degree. So then, like, to count 1 per vertex, this gives me C times V, and to count in degree per vertex, this gives me C times E. So overall, this is C times V plus E, which is linear, right, in the representation of the graph. Okay, so this is an algorithm that we saw earlier, right? We haven't solved it exactly like that. We solved it, using the update method. but essentially this is how we solved it, right? So it's exactly the same solution. We just are looking at it a little bit differently by defining this subproblem, defining a recurrence, and sort of analyzing how much time it takes us to solve each subproblem, given the previous ones. Maybe an important point here is that what will be the order of the subproblems? In which order would we solve them? We will solve them according to the topological sort on the DAG, right? So we want to know, when we analyze the vertex V, we want to know the distances to all previous vertices, you know, all the ones that point to it. But this is exactly topological sort. Topological sort ensures us that we are putting all the vertices on a line and all edges go from, you know, left to right. Okay. So, okay, so this was like a lot of fuss on just doing something that we already know. But I want to say that now it's very easy to modify this problem. So this was a very general framework. And now what if I want to find like the longest path in a DAG? What would I need to modify in my algorithm? Right, so a longest path is a path. Every path has, you know, every path going from S to V needs to go through some vertex U such that UV is connected, right? So here we can just replace this mean with a max. Okay, so you can see that this is a very powerful technique, and it allows us to do more complicated things than just, you know, taking the shortest path or like just applying means. We can do max, we can do sum, we can do a lot of stuff. So we can combine all the previous solution in a sophisticated way to get a solution for the bigger problem. Now, so here, recall that the goal was to find the shortest path from S to T. So here we solved all these subproblems. Eventually, we'll need to output the you know, the solution to the problem that we were given. Right, so here it's longest. So we'll run this algorithm, and in the end, we'll output the distance to T. Right, the distance to T is one of these subproblems, and we are solving that. We are in particular solving that. We are also solving other problems along the way. Right. So that's okay. So that was a shortest paths or longest path in a directed acyclic graph. Okay, so let's call this problem 1, because this is maybe the first interesting problem that we have solved. Okay, so now I want to move to problem 2. Yeah, sorry, I think there were a few questions, so maybe it's a good time to stop for questions. So you can unmute yourself or raise your hand. Okay, so any questions on that?
Oh, so Professor?
Yes.
Oh, when we're finding the shortest path in a DAG, are we using Dijkstra's?
No. So this is the algorithm that we're using, right? So I wrote that.
What is the algorithm though?
The algorithm is this. We are linearizing the graph.
Yeah.
Okay? And then we go over the vertices one by one. And every time we are applying this one line.
Oh, so you just like start from the start and you just expand out applying this formula, right?
Yeah.
Oh, okay. Thank you.
Right. So this is very similar to what we had when we talked about Bellman-Ford. Then we talked immediately after about shortest path in the DAG. And
oh, right. Yeah.
it was just one iteration of Bellman-Ford where we pick the order in a smart way, right? So if you go over all vertices according to the linear order, to the topological order, then you just need to do one iteration over update to get all the correct distances, right? Yeah. So notice that this is actually faster than Dijkstra. It runs in time order V plus E. It handles negative weights. but you need to assume that the input is a DAG, right? So that's like the best, it's the best that you can do because it's run in linear time and it handles like everything that you want, like positive, negative weights, but you have to assume it's a DAG. So it would be nicer if we have something like this exist without the assumption. Okay. Okay, so
I think there's a question. Somebody
sorry?
I think there was a question somebody tried to unmute.
Yeah, I was wondering if why we also wanted to handle negative weights. Like, is this just the problem statement, or because I remember based on like we were trying to form this question to solve something else about the directed acyclic graph on the edges and nodes that represented our dynamic programming like runtime.
Yeah, no. So this is a problem, right? So dynamic programming is a algorithmic technique that you can apply to many problems. You can solve with it many different problems. We will see how to solve problems in biology, how to solve problems in on strings, so on and so forth. So here I'm sort of revisiting shortest path in a DAG, which is a problem that we already talked about, and I'm rephrasing our solution as a dynamic programming solution, right? What is a dynamic programming solution? You look at the big problem, you identify a lot of sub-problems, you show the connection between these sub-problems using a recurrence, and then you show how to solve these problems from small to large, and you argue about the running time of this thing. So this is just doing that. Okay, so the collection of sub-problems is the shortest path from S to V for any vertex. The recurrence is this thing. There were a few edge cases that we needed to do, and then we analyzed the running time, and the running time was overall linear. Yeah. Okay, by the way, I forgot to talk about memory. What's the memory required for this algorithm? Well, I'm just storing one number per vertex, so it's order V.
We also have a question from the Piazza asking what an example of a problem where you would want the longest path in a DAG would be.
Yeah, so the next one. So it will be very clear once we talk about the...
Okay. Professor, I have a quick question.
Yeah.
If you assume that G is not topologically sorted, I feel like the runtime could go up if you have to topologically sort it in the beginning. Is that a possibility, or do we just
right? But we know that the topological sort can be done by DFS, so it takes also linear time, right?
Oh yeah, so yeah, okay, thank you.
Right. So yeah, it's a good question because we have to assume something about the order of the problems, so that when we compute this recurrence, we need to have all these distances to U ready. If they are not ready, then we cannot really compute. This would be ill-defined.
So how can we think development for the SADP problem?
Yeah, okay, we will see. We haven't seen it yet, so we'll see it later. Okay. I just gave it as a teaser. I haven't explained it yet. Okay. So I see that we are running out of time. So maybe I will just tell you what will be next time. Okay, so next time, I hope that I will be able to cover all these things. These are many very cool applications to dynamic programming. So the first is longest increasing subsequence. So this is a problem where you're given a sequence of numbers, one, let's say 1, 3, 2, 4, 7, 5, 6, and you need to find the best subsequence. It doesn't need to be consecutive, so you can pick like this one, this one, this one, this one. You want the subsequent to be increasing, and you want the longest one. Okay, so in this case, this is, I believe, the best one. You can do greedy approach. You can, every time you can, pick the first element that is bigger than everything that you already picked. But this would give you like this one, and then this one, and this one, and then this one, which is shorter. So greedy would not work for this problem. And we'll show how to use dynamic programming to find the solution in quadratic time, in time order n squared. And it's also possible to view this solution as finding the longest path in a DAG. So you can also rephrase this question as a question about DAGs. Then we're going to talk about maybe one of the most important applications of dynamic programming, which is edit distance. This is used a lot in computational biology. You can use it to align DNA sequences. So if you have two sequences, maybe one has a few mutations on the other, you want to sort of put them one next to the other and sort of do it in a way that has the least number of inserts, deletions, and swaps, sort of character changes. So we will show how to compute this optimal way to go from one string to another. You can also, another application of this edit distance is for spell checker. If you're writing, some word and you make a typo, then usually Gmail or whatever would suggest to you another word which exists in the dictionary, exists in the, let's say, English language, and has the smallest number of changes between your word and this word. So this is really what Gmail is doing, sort of going over all words in the dictionary and computing the edit distance and picking the one with the smallest edit distance. So this is super useful there as well. You can also think of it as finding, plagiarism, finding if someone copied a piece of text from somebody else. And you can also solve it using this thing. So this is really super cool algorithm that has a lot of application. We would also talk about two NP hard problems, the knapsack problem and the traveling salesperson. In knapsack, you are sort of robbing a bank and you have a limited bag and you want to put as much valuable stuff as possible because you eventually want to sell these. But unfortunately, the bag is limited. Maybe it can carry, I don't know, like 10 pounds of products. So you are limited, and you want to find the best way to do that. In the traveling salesperson, you want to travel between, I don't know, all the cities with more than 1 million person in the United States, and you want to do it in the shortest way possible. And hopefully we'll have time to show that you can do it not in polynomial time, but you can do it in exponential time. Whereas if you think of it naively, it will take you something like n factorial, which is much larger than exponential. And there are more examples, I guess, probably will not have time to cover all of them, but really this dynamic programming approach is solving many, many interesting examples. So hopefully we'll see many of them next time. So that's it for today. Let's finish stop the recording, and feel free to stick around for a few minutes and ask some questions if something was not clear.
Professor?